Okay, well, first of all, I wanted to thank the conveners for inviting me to speak at this conference, though I have to say that one of the crueler things you can do to me is invite me for a talk at Yosemite and then schedule the talk right at sunset. But never mind. For a number of years now, we've been looking at geomagnetic storms by running a global MHD simulation combined with particle tracing, which we call the large-scale kinetic technique, to understand the acceleration, transport, and energization of ions in the magnetosphere during these events. And the questions that motivate me tonight are going to be, how does the sudden storm commencement of CME storms affect the ion distributions in the inner magnetosphere? How are ions energized and ejected? And then what are the similarities and differences between CME and CIR storms? And to do that, what I'm going to do after presenting my methodology is to look at two case studies. First, the October 28, 2001 CME storm, and then the March to 9th, 2008 CIR high-speed stream storm. So just to go through my approach in about 30 seconds, now that I have 10 minutes less than I thought I did, we start out by running a global MHD simulation of an actual event using upstream solar wind and IMF data from whichever spacecraft is sitting out there. So we have the global fluid physics in this MHD model. And then we follow the orbits of nowadays billions of ions in the time-dependent electric and magnetic fields, which we've obtained from the MHD simulation using the full Lorentz force equation. And so we're attempting to put a bit of kinetic physics into the global model. And for the purpose of these studies, we launch H+ ions from the solar wind and O+ ions from the ionosphere. So the large-scale kinetic technique is nothing but particle tracing taken over a very large number of particles, and we use the Lorentz force equation to follow the orbits of the particles throughout their orbits. We don't switch back and forth. For the solar wind, we launch a wall of ions at the magnetosphere upstream of the bow shock at x is about 17 RE. We do this at 1-minute intervals, starting 2.5 hours before sudden storm commencement, 2-3 hours before the first CIR arrives for our CIR storm. And we place 100 ions per grid point on an 80 by 80 RE grid centered at the midplane. And that gives us about, I think that's, so it's about 2 million particles per minute, then makes about 1 billion or 2 per launch. We launch the ions every minute based on the spacecraft observations of solar wind speed, solar wind temperature. And so we were able to then use these to calibrate densities and other parameters inside the magnetosphere. For the ionosphere, we're still using the Strange-Way et al. Outflow formulas with an asterisk on it that I'll explain to you in a bit. What we do is we take the two formulas, one for precipitating density and the other one for downward pointing flux, plug them into our MHD ionosphere and obtain outflow rates for the O+ ions. And we actually launched 2 separate simulations of O+, one with the precipitating density and the other one with pointing flux. As you can see, they're very, very different regimes that the particles are being launched from. And then for the densities and everything else that I'm going to show you, we take the quadratic mean of the 2 runs taken together. So let's talk about the October 28, 2001 storm. Let me zoom in instead of having you squint. For that storm, the important parameters, and this is geotail sitting just upstream of the bow shock. We have a BY which starts positive and goes strongly positive when the CME strikes the Earth at about 320 UT. That's the red line. BZ is southward and goes more southward. VX has a jump, and the dynamic pressure has a modest jump. The density in the solar wind isn't that high, so we get about 6 or 7 nanopascals of dynamic pressure. Let me zoom in again. Inside the magnetosphere, what we're getting is AE, AU, and AL. AE is red, AL is black. And you can see that following the storm onset over here, we have a whole lot of activity, and it's difficult to pull anything out of here. Bob McFerrin was nice enough to sit with me couple of years ago and pull out all of the substorms. There's a major one that happens at 4:30 UT, a couple of them that happen at just after 6 and just before 7 as well. But it's very, very active throughout this time. Now, when we plug in these parameters into the MHD model and use Strangeways formula, what we get for the ionospheric outflow is pretty reasonable. With the red curve is the Poynting flux outflow integrated over both hemispheres, and the black curve is the electron precipitation. And you see both of them jump by a factor of 5 or 6 right when the CME hits, and then other things take over internally. You see this increase in Poynting flux outflow as the event progresses. Now, the question we have is, how much of this is geo-effective? How much of it does it actually make into the ring current and plasma sheet? And I've started coming up with a new plot to do that, and I'm going to walk you through it because it's going to take steps to assemble it. So what I have for the 6 hours of our simulation, the percentage of particles that reach the plasma sheet, that's the red curve, and it's defined between 10 and 30 RE in the tail. Y is plus or minus 7 right in the center. And the ring current, the night side ring current, which I define as radial distances between 3 and 8 RE, and the night side, nothing on the day side. And so we've got the Poynting flux outflow out here, electron precipitation outflow down here. Now, I'm going to put everything together so you can compare it to IMF parameters and the dynamic pressure, but let me step you through them. As you saw, the IMF BY isn't that exciting for this event until you get to about 5:30 UT. BZ, similarly, there's lots of fluctuations, but it's strongly southward throughout the event. Dynamic pressure, well, we've got this. So let's try to put it all together. So if I put the geoeffectiveness plot together, the only external thing I can think of, aside from those fluctuations, is the actual impact of the CME. And that's over here. And well, we can see that that, in fact, influences how much O plus from primarily the night side reaches the plasma sheet and somewhat the ring current. But that effect, as we'll see, is eclipsed by the sheer number of particles that is coming out. This feature over here is actually a flux rope that sits right in the center of the tail, and it prevents access of ions to that part of the plasma sheet. Ions go either deeper or closer in. As you can see, there's a jump in the ring current, and there's a drop in the plasma sheet axis. Okay, now I have a number of movies to show you, but I'm going to select portions of them. What you're going to see here is the conglomeration of all of our LSK results. What we're going to be looking at is the equatorial plane, which is the plane of maximum pressure in our MHD code and on the night side, and z equals to 0 on the day side. Actually, for these runs, we had that for some reason at x is minus 2 RE. So sometimes you're going to see a pretty sharp gradient at that point. That's just because we're switching from one plane to the other, but I want you to concentrate on the tail. At this point, again, this is solar wind H+, ionospheric O+ with particles per cc density, and this is energy density in keV per centimeters cubed. At this point, we've been launching particles for 2 hours already from the solar wind and from the ionosphere, and you can see that solar wind particles have started coming in, but they haven't made it all the way across the tail. Ionospheric particles are a captive audience. They're already in there, but you can see that very briefly, the O+ partial ring current on the night side exceeds in density from the solar wind, but the solar wind is a lot hotter than the ionospheric particles. Let's run through this until maybe an hour after the storm. Again, I don't want to take all of my time doing movies, and slowly but surely, ions primarily from the dawn flank will come in and will populate the tail as far as the solar wind is concerned. And the next event we're going to see is the actual arrival of the shock at 320. You can see that down here, there, and that's going to be a big chunk of ions coming in, immediate increase in the night side ring current, lots of high energy density in the near Earth tail and partial ring current, modest increases in ionospheric O+. And for this storm, which has a DST of about minus 150, the O+ never really gets to be dominant in the near Earth tail or night side ring current. Okay, I want to stop this because I want to zoom in closer to the Earth. This is that same data, but taken at a radial distance of 8 RE and closer. again, we have H plus density, O plus density, and the energy density is down here. Each one of these circles is at 2 RE, 2468. So this is fast forwarded to 20 minutes before the CME impacts the Earth. You've already got somewhat of a partial ring current for the H plus. You've got a full, very cold ring current for the O plus. And now let's go through this. And we're going to see two things. First of all, when the storm hits at 320 UT, you see a broader partial ring current here, and you can see that very quickly it fills out to be a complete ring current on the day side as well. O plus densities are elevated, but not as high. A second increase is going to happen at 430 UT when the substorm that I talked about hits, and there you can see, again, more injection. Because of the color scale, you can probably only see it on the day side. And then throughout the event, what you're getting is various injections, O plus and H plus, never at the same time, never in the same location. And you can see that the peak of the O plus energy density, for example, is sitting right at dawn and right at dusk with a nice partial ring current sitting here. And by the end of this movie, you've got a more or less complete ring current at very high energy densities. Okay, now what I'm going to do is I'm going to zoom in to this plot that we just looked at. And I'm going to pick out the night side ring current, that area between 3 and 8 RE on the night side, and I'm going to look at the energy densities in the ring current for this region. And in this plot, what I've shown is the average over that entire area of ionospheric O plus, which is the blue curve, the solar wind H plus, which is the red curve, then the total of the solar wind and ionospheric particles, that's green, on a log scale with the MHD density in there. And you can see that, oops, let's go back. I should have had the other circle first. That the MHD and LSK agree pretty well up until about 430 UT. After that, that's the substorm onset. And after that, you can see that the ring current energy density due to LSK particles increases greatly. The MHD, which doesn't have a ring current, does not respond, and it just keeps going flat. So that's what the circle was all about. Now, if you compare this to dynamic pressure, you see that the jump in dynamic pressure is almost accompanied by a linear increase in every single one of the parameters that we show here in energy density. So the ionospheric O plus reacts instantly. That's particles that are already in the lobes or en route, and they just get pushed in. Solar wind H plus responds immediately, so does the MHD, and you're getting a jump that's the same order of magnitude for all of these. Okay, now a couple of things to do to make sure we're actually simulating the real magnetosphere and not just a fairy tale. And we've done two comparisons with observations. The first is with image HINA, which was looking at a pretty oblique angle at the magnetosphere at this time. And with the help of Pontus Brand, actually he did all the work here for this part, he took the image HINA images and converted that to energy densities, as shown on the right. One of the assumptions, one of the many assumptions that went into doing that was that the plasma distributions were isotropic. And then he took our data, our LSK distributions, and constructed in the exact same energy range for the H plus, the distributions from LSK. And as I step through this, this is going to be every 20 minutes. This is before the storm hits. This is right at storm onset. And 20 minutes later, and let me stop it there. So at this point, we're doing a pretty good job of the increase of the energy density in the ring current. But what the LSK is showing is this tail going towards the day side, which happens to be the primary source of our ions for the ring current at this time. The image HINA doesn't see that. And when I talked to Pontus, he was telling me that that's probably because of the assumptions that are made in this. So we had to do another check. In fact, I'm going to go through this. That check is thanks to the LANL satellite, LANL 1990-095, which starts in it's in geosynchronous orbit, starts at 0200 UT, so before the storm onset, right over here, and by 0700 UT, which is the end of our simulation, it's in the dawn flank. This is one of the hardest areas for us to simulate. Ions are usually going down to tail and convecting duskwards. But when you do a comparison, black curve is LANO, green and red are our LSK particles, and they're on top of each other because the ionospheric contribution to that quadrant is very, very little. This is the Dawn flank, and you can see that within a small error bar, we're doing actually a really good job of duplicating the densities measured by LANO in that flank, so that tongue of plasma that you saw coming from the Dawn flank and entering the ring current is actually being seen by LANO as well. Hopefully I haven't used up too much of my time. Let's talk about the 8 March 2008 storm. This is a very, very prolonged event. It starts with the arrival of a CIR at about 7:20 UT on 8th of March. Here's that CIR over here. In fact, I think I have, yeah, there we go. It's a density enhancement, and after that, there we go. There's a small jump in the solar wind velocity. Over the next day, the solar wind velocity gets higher and higher, and in fact, we have a second CIR that arrives at about 140 UT on the 9th of March, and that's when the real storm starts. And you can see a lot of alpha-vanic turbulence in the tail during the second part of the event. So looking at the geomagnetic indices for this day, we have the initial phase where SIMH is going positive, and then due to 2 disturbances going negative finally. We have 2 large substorms that happen during that time. And then when the second CIR hits, that's actually when DST hits minus 100 approximately, and we have this prolonged period of activity in the tail. Now, when you plug in all of that, our MHD simulation, which I'll actually talk about in detail in the second talk, which my students was supposed to give, but I'm stuck with now. When you plug that, the Strange-Wei et al. Formulas for this event, we get an ionospheric outflow that's about 100 times stronger than it should be. So what we've done is we've put an upper limit on the amount of outflow we have using the Moore et al. 1999 parameters that link the maximum outflow to the standard deviation of solar wind dynamic pressure. So that's the blue curve that you see. So anytime any of our curves exceeded the blue curve, we brought it down to that value. Again, if we look at geoeffectiveness, now you see that it's a lot more variable than the CME storm. Again, I'm going to go through the same steps, looking at these one by one. If we look at IMF-BZ, there are a number of southward turnings here. And so I can shade gray the regions which are southward turnings of the southward IMF regions. Dynamic pressure has 1, 2, 3 increases. The first and third are the 2 CIRs that arrive, and here's a smaller increase in between. So now if I take these and line them up and zoom in, this is what you get. And the question is, can we really pick out things that are happening to the axis of ionospheric ions due to external stimuli? Yeah, we can go in there and say, okay, with this jump in dynamic pressure, we get a jump in access, but then there's this one which has nothing to do with anything. Some of the southward turnings result in a lower access into the ring current, some don't. But we have to really look at this carefully and see what are some of the factors that are going into this. Okay, so I have a similar movie, and I think I'm right on time, except that this is a pretty long movie. It's a long event. What we've done is, this is the longest simulation we've ever done. We started at 0400 UT on 8th of March, and we went all the way through the 0800 UT on the 9th of March, right after the main phase turned into the recovery phase of that storm. And you can see now we're inside the first density enhancement, and already what you're seeing is H+ particles from the solar wind have started making it in. They've started going all the way around. The scales, they're impossible, I'm sorry, to read, but the O+ scales are lower, so this does not correspond to the same density. It's a factor of 5 lower, if I remember. But by the time we get to the highest point of this the first CIR, we've got a pretty strong partial ring current, and you can see the energy density is pretty high as well. Get to the second to the high-speed stream event, and I think I will stop this movie at that point because I want to make some concluding remarks. But we have this simulation run for the entire 30 hours or so, and we have a wealth of data that we're gathering from it. What I want to do is actually show something interesting. If we now take, like I showed you before, the region we call the plasma sheet between 10 and 30 RE, and Y is plus or minus 7, and our ring current, and look at densities and energy densities. I showed you energy densities for the CME storm before. Here's, with the same color coding, densities and energy density, let's see, ring current density and ring current energy density for the entire event. And what I want you to see is this part here, that after the first substorm, at about 1200 UT, and in fact, especially after the high-speed stream arrives at about 1830 UT, what we have is a ring current, at least in the LSK, which is as strong as the ring current we had for the CME storm. In fact, it persists for a lot longer. It's from about 1800 UT, or even earlier, all the way to 0800 UT, which is the end of our run. So I am on my 2 summary slides, right on time. So for the CME storm, what we saw were multiple energizations and injections during the first 4 hours, which we've modeled, but that the H plus and O plus injections were usually not simultaneous. The jump in ring current energy density was a linear response to the solar wind dynamic pressure. The solar wind dynamic pressure increased, the energy density went up, and I'll talk a bit more about that in the second talk that I'll be giving. And that I didn't go into much detail except with the observations here that the down flank was in fact the source of hot plasma for the ring current through a region we've published on before, this gash of particles coming in, which Benoit Levroy has also seen with LANL data. And we saw very good agreement between not only image HINA but also the LANL observations. For the for the CIR storm, which we're still working on, there's an incredible amount of complexity in the solar wind and IMF. I'll be showing you a movie of the MHD simulation. You'll just see that there's nothing that's steady in the entire 30 or so hours of the simulation that we've done, and that we got a ring current out of that model for the LSK, which persists for a very, very long time at intensities which rival that of the CME storm. And that's all I have today.
Questions for Vahe?
Hi, Vahe. I
Hi.
notice you get very intense ring current. I was wondering, do you have any losses in the system?
I don't have charge exchange. There are 2 losses, precipitation into the ionosphere and losses to the dayside magnetopause. And the dayside losses to the magnetopause as the bow shock goes in and out and pushes the magnetopause in and out, that's the primary source of loss in our system. Right, well, yeah, we try not to, we've been hit on the head enough times for doing that we kind of don't make any conclusions about inside geosynchronous. I think at geosynchronous, we're not going to have charge exchange lifetimes that are that long, so we don't include them at this point.
This is just informational. Did you say what the DST was for the 2 storms, and did you do any comparison of your results with DST?
I haven't computed DST from my results. The CME storm was DST minus 150, and the CIR storm was minus about 100.
You mentioned at some point, if I heard correctly, that a plasmoid had formed or flux rope had formed and was influencing the transport of the particles. That's something I've been interested in. Could you expand just a little bit in terms of the mechanism?
Well,
exactly what you saw?
Well, when I show you the MHD movie for that day, you'll see that there's a lot going on. That this notion that ions come out of the ionosphere or from the solar wind, convect down the tail, hit the plasma sheet, and then slowly and surely come, does not happen in the real world. What's going on here is there's so many changes going on. The reconnection site is constantly moving, and flux ropes are forming because there's an IMF BY and BX, and that this steady convection or access of ions from the tail to the night side ring current simply half the time doesn't exist. In fact, for several of our CME storms, we've seen that if you have an IMF BY, what you get is an access region on the dawn side, somewhat like the sash that George Sisko talked about, that actually injects ions right into the ring current before they get to the plasma sheet. So the path isn't solar wind, plasma sheet, ring current. It's solar wind through the low latitude boundary layer into the ring current as it's entering the plasma sheet as well.
I'd like to talk to you later.
Definitely.
I was going to say, I think in the interest of time and kind of catching up a bit, we're going to move forward. But thanks, Vahe, once again.